Hello. Hello, everyone. Right. Okay, so today is a new topic. Today's a new topic, and it's momentum. Okay, so I'm sure you've done momentum in year 11 or year 10 sometimes. So you should know what momentum is. You should know what impulse is. And well, I won't be telling you anything new today, but I will be going into momentum much deeper than you're used to. Okay, so who has done momentum in year 12? Has anyone done momentum in year 12? Good. Doing it now. I have good. And if no, can you tell me no? Okay. Just one no? Good. Okay. So all right, I'll share my screen and let's get going. That's promising. It's promising that most of you have done momentum in year 12. So that's good. Right. So first of all, we need to be able to prove the conservation of momentum. Okay. So let's say we have three bodies, three objects. So yeah, I'll just quickly remind you, the momentum is defined as mass times velocity. Momentum is mass times velocity. So momentum is a vector. What else do we know? We know that the change in momentum is called the impulse. So also a vector because it's a change of a vector. So that's impulse. So this is momentum. Which is a vector, of course. And impulse, which is also a vector. Okay, and that the change in momentum divided by change in time is force, which is the resultant force. This is another way of writing Newton's second law, which is force. Which is also a vector, by all means. You can rewrite this and write this delta P, which is force times delta T, or in other words, the impulse is force times delta T, which is another important formula. Okay, and as a matter of fact, as we will show later today, that impulse is also the integral of force dt. Yeah. You can see that these are actually very similar. It's not a coincidence, right? So if the force is a function of time, then the impulse or the change in momentum, I'd rather say change in momentum, because change in momentum is for the force. So for example, let's say the force starts with 3 newtons and then decreases by 0.1 newton every second. Yeah, so this is a force which depends on time, which is a function of time. So it starts with a force of 3 newtons and then decreases by 0.1 newtons every second. This is what this says. And the change in momentum caused by that force will be the integral from 0 to, let's say, acts for 5 seconds, 0 to 5 of 3 minus 0.1 t dt. I'm not going to integrate this and explain the consequence of that, but this is an important thing. So if you, just maybe look into this. The change in momentum is the integral of force with respect to time. Okay. Oh, I don't think we'll. Isn't the integral of force just momentum, not change in momentum? Oh, no, because a force changes momentum. Newton's second law says the force is a change in momentum. Interesting question. Well, look, let's say you are traveling at a velocity. Let's say you have a mass of 2 kilograms and you're traveling with a velocity of 3 meters per second. Then this force causes you to change momentum. And you can find your new momentum as the initial momentum plus the change in momentum plus the integral. So your momentum will depend on your initial momentum, and initial momentum is not a thing in here. Change in momentum is the final momentum minus initial momentum, which is equal to the integral. So the final momentum is the initial momentum plus the integral. So no, your way of thinking is not correct, Alistair. Does that make sense? So the integral is just the additional momentum that you gain from the force. So if you're not moving, yes, it gives you your momentum. If you're stationary and there's a force acting on you, you can find your new momentum by integrating it. But it's the same thing as saying that the initial momentum is 0. Therefore, your momentum is the integral. Yeah, so like that. Anyways, we've gotten from the very start, we've gone very deep into it. That was not my intention. I just gave you a sneak peek of what we are going to do in the next 4 weeks, as a matter of fact. So this assignment, you're given 4 weeks to do. So use your time wisely. It's 14 questions. And the question number 14 is incredibly difficult. So I challenge you to bring me the solution of question 14 to the next webinar. Well, next week is going to be maths, but the week after, so the 20. Right. 14th of February. Okay, so let's say we have a system of 3 objects, and each object these objects interact. So let's say that object M1 exerts a force on M2. Let's say this is an attractive force. Doesn't really matter what kind of force it is. And we say this is the force exerted on object 2 by object 1. Now, according to Newton's third law, we have an equal and opposite force on object M1. And that's F1, 2. So it's the force on object 1 from object 2. Now, object 2 and object 3 also interact. And let's say it's a repulsive force. We don't know the nature of that force, but we're not really interested in that. And let's say this is force on object 2 from object 3. And this is the force on object 3 from object 2. And well, not finally, but furthermore, let's say there's a force similar. There's an interaction between object 1 and object 3. So this is F. So this is F1, 3, and this is F3, 1. We got the arrows. Okay. In addition to that, there are 3 external forces. So let's say there's an external force on object 1. There's an external force on object 3, and there's an external force on object 2. So F1 external, F2 external, and F3 external. Does this make sense? Are there any questions about this diagram? No questions? Is anyone confused? Utterly or utterly-ish? Good. So we write the Newton's second law. Newton's second law. Second law. For object, oh, we don't know. It could be gravity, it could be friction. Doesn't really matter. Any external force. Yeah, somebody's brought a magnet and it's pulling M1 with a magnet. Somebody is physically pushing M2 and somebody is doing something to M3. We don't know. That doesn't really matter. Newton's second law. So Newton's second law is mass acceleration equals resultant force. So for object M1, M1A1 yes, M1A1 is equal to F21 plus F12, F13 plus F1 external. For the second body, M2A2 is F21 plus F23 plus F2 external. Then M3A3 is equal to F31 plus F32 plus F3 external. Okay. Then we know that F12 is equal to minus F21. F13 is equal to minus F31. And F23 is equal to minus F32. According to Newton's third law. Does this make sense? How much sense does everything makes so far on a scale of 1 to 10, please? 10 being it makes perfect sense. Good. So now we add these three equations together, and we have M1A1 plus M2A2 plus M3A3 equal. Now you see F12 and F21 cancel. F13 and F31 cancel. And F23 and F32 cancel. And we got F1 external plus F2 external plus F3 external. We will write this as the sum of external forces. The sum of external forces. And here we will remember that acceleration is change in velocity divided by change in time. So M1 delta V1 divided by delta T plus M2 delta V2, these are vectors, of course, delta T plus M3 delta V3 divided by delta T. And we can say that M1 delta V1 plus M2 delta V2 plus M3 delta V3 is equal to sum of the external forces multiplied by delta T. And if you are, if you've noticed that M delta V is actually delta P1, the change in momentum of the first object, plus change in momentum of the second object, plus the change in momentum of the third object, is equal to the sum of external forces multiplied by delta T. And that means that if the sum of external forces is 0, so that means if there are no external forces or the external forces add up to 0, yes, so if there are no external forces or, so no external forces, or the sum of external forces is 0, then this the total change in momentum, delta P1 plus delta P2 plus delta P3, is 0. So remember the conservation of momentum. If there are no external forces, the total momentum is constant. So we have just proved mathematically the conservation of momentum. If there are no external forces or 0 total external force, the total momentum of the system is constant. Cool. Do you understand every step on a scale of 1 to 10, please, again? Okay, perfect. Yeah, so we've just mathematically proved conservation of momentum, and you can also say the momentum of the system cannot be changed by internal forces. This is another way of saying momentum of a system cannot be changed by internal forces. Total momentum of a system cannot be changed by internal forces, which is not the case for the kinetic energy, for example, because the kinetic energy of a system can be changed by internal forces, but the momentum cannot. And I don't know if I've told you, but there was a proposition of building a rocket which had the shape of the letter D. Okay, and there was a pump. Okay. Oh, you remember talking. So I'll just quickly remind you. There's a liquid passing through, and because the liquid is going in a circle here, so here it's straight, so there's no centrifugal force on this straight bit, and there is a centrifugal force on this bit. And the idea is that the rocket will propel itself. But this force is an internal force, and an internal force cannot change the momentum of a system, the total momentum of a system. Therefore, this rocket cannot propel itself just based on this simple fact. The total momentum of a system cannot be changed by internal forces. The reasoning that it won't work because there's a force in here as well and here as well, which cancel out. I won't go too deep into this. You can rewatch one of the previous webinars. I go into more detail. Rocket cannot travel due to internal forces. Okay. So let's do some examples. So problem 1. Two objects of mass m2 and m1 collide head-on. Okay, so we always start with the diagram. Two objects, mass m2 and m1 collide head-on. M2. M1 is initially traveling with speed v. M2 is at rest. Okay, M2 is at rest. The force of interaction is given on the graph. Find the velocities of the two objects after impact. So head-on means it's a central hit, because if they hit off-center, they would travel in different directions. But when we say head-on, means it's a central hit. Okay, the force of interaction is given on the graph. Find the velocities after impact. So we know that the momentum, so the change in momentum, is equal to the integral of the force with respect to time. Or, in simple words, it's just the area under the graph. Yes, so T1, T2. Because the integral is the area under the graph. Okay, so delta P, the change in momentum, is 1/2. So it's a triangle multiplied by the height of the triangle F0 and multiplied by 2T0, which is the base of the triangle, sorry. So it's F0, T0. The change in momentum of the first object. Now, is it though? But because when they collide, the force of collision, so the force of collision, so when they collide, the force is this way, and the force on M2 is this way. So we have F and F. Well, in this case, it's, well, minus F. Or okay, it's F1 and F2. They're equal and opposite. So the force on M1, so the delta P1, the change in momentum of the first object is going to be minus F0T, T0. And the change in momentum of the second object, because the force is to the right, and it's the same force for the same time, is going to be F0T, 0. And we can see that delta P1 plus delta P2 is equal to minus F0T0 plus F0T0, which is 0. So 0 total change in momentum. Okay, so it works. Now, the momentum P1 after, so we will indicate that P1 is before, P1 prime is after. Momentum before, and P2 and P2 prime. So P1 and P2 is before P1, P2 after. Sorry. Therefore, we have from here, let's be smart about it. So delta P1 is P1 prime minus P1. Prime means just a dash, P1 dash. P1 dash is after. It's not the derivative. It's not the derivative of momentum. The derivative of momentum would be the force. Plus P2 dash minus P2. So that's the change, because delta P is defined as the final minus initial. Yes? Equal 0. And here we have P1 dash plus P2 dash equals P1 plus P2. That is the same as saying momentum before equals momentum after. Yeah, momentum before equals momentum after. So we're still doing the same thing. So momentum before is m1v plus 0 equals momentum after oh, sorry, we don't need that. Okay. So the momentum of the first object, for the first object, P1 dash minus P1 is equal to minus F0 T0. Therefore, P1 dash I think I've made things unnecessarily complicated. And I'll delete this. After. So before collision and after collision. So before collision is M1V, and after the collision, it's a M1V1 and M2V2. Okay. So assume that. And therefore, we can write that M1V1 minus M1V is equal to minus F0 T0, because that's the change in momentum. Final momentum minus initial momentum. We can divide by M1 and get V1 is equal to V minus F0 T0 divided by M1. So that's the velocity of the first object after the collision. And then P2 prime. No, M1 slows down because of the collision. And P2 will speed up. So P2 prime minus P2 is equal to so this is the initial equation. Okay, then this is the initial equation. We rewrite it like this. And then we rewrite it like this. And when we rearrange it, this stays still minus. No, it's not plus. This is minus it from the very beginning. This becomes M1. I can say that this is. So if you rearrange equation, that's what you get. Does that make sense? Yeah, you keep the impulse negative. All right. Does this clear things up? Okay. P2 prime minus P2 is M, which is M2V2 minus 0, and that's equal to F0 T0. Therefore, we can simply write that V2 is F0 T0 divided by M2, and that's the answer. Okay. Okay, problem 2. A spaceship before detachment of stage 2 had velocity v. After detachment, the velocity is 1.01 v. Okay. So it's phrased slightly weirdly. So basically what it says, the spaceship consists of 2 stages. So stage 2 and stage it's usually numbered the other way around. So stage 3, stage 1, stage 2, stage 3 of a rocket. Anyways, before detachment of stage 2 had velocity v. So before the whole rocket is traveling with velocity v. Okay. After the detachment, we have stage 2 detached and the stage 3. And this is traveling at 1.01 v. The second stage moved with velocity 0.04 v relative to the ship. And that's a key piece of information. So it's not moving at velocity v. So what is the velocity of this stage? And once you answer this question, everything becomes super easy. It is not 1.05 v, no. Otherwise, it would be going faster than the front of the ship. Vin, no, that's incorrect. Look, this is the front of the ship. This is where the astronauts are. Yeah. Mm. This is a second stage with fuel and a booster. Louis, yeah, yes, that is correct. 1.01 minus 0.04, which is 0.97 v. Because the relative velocity is 0.04. Therefore, it is traveling at 0.97 v, and this is traveling at 1. So the relative velocity is 0.04, which is correct. Cool. Now the total mass of the ship is m0, and they're asking for the mass of stage 2, and we'll call this m3. Yeah, because technically it is stage 3. So we know that m2 plus, m3 is equal to, well, we don't have to do this. We don't have to introduce m3. Let's make our life easier. m3 is m0 minus m2. Okay, it's the mass of the whole rocket minus the stage m2. We're assuming that we're not losing any fuel, so we can do that. They're connected by springs, and sometimes they might be. Okay, so I have momentum before equal to momentum momentum after. So we have m0v is equal to m2 times 0.97 v plus m0 minus m2 multiplied by 1.01 v. Okay, and the beautiful thing is that v cancels out. So we have m0 equals 0.97 m2 plus 1.01 m0 minus 1.01 m2, and we get 0.01 m0 is equal to 0.04 m2 because m2 is equal to m0 over 4, and that is the answer. So look, the tricky bit here is figuring out these values. Figuring out these values. Because once you figure them out, it becomes just a walk in the park. You just plug it in to the equation, and it's not a physics question anymore. Yeah, physics ends here. So everything up to here is physics. Everything else is maths. Any questions? Any questions? How well do you understand this problem? On a scale of 1 to 10 again, please. Okay. Would somebody want to tell me why 9? What's the little thing missing from your understanding here? The relative part. So you're still confused about the relative part. The relative velocity means that if you are sitting inside the rocket, you will see the other part of the rocket traveling at 0.04. That's what relative velocity means. If you're sitting in one of them, you see the other one moving at 0.04, which is not the same as the velocity that you have, your overall velocity. So for example, on a motorway, if you have two cars, one traveling at 60 and the other is traveling at 80. Oh, no, sorry. Cars on the motorway never travel 80. 70. Right. And the car that if you're sitting in the 60 car, the relative velocity is going to be 10 of the other car is going to be 10. And if you're sitting in the 70-mile-per-hour car, the velocity of the other car would be minus 10. So it's going in the other direction, backwards. Relative velocity. Relative velocity is 10. But if you're standing here, one is traveling 70, the other one's traveling 60. What is the difference between physics and maths? That's such a philosophical question. Look, to a mathematician, if you give this equation, to a mathematician, they will be able to solve it without any information about what is M1, what is M2, what is M0, what is V. They don't care. It's a set of mathematical rules which leads to an answer. So you can solve this. You can solve this equation without any knowledge of what these letters stand for. Now, when you do physics, you have to define the letters. You have to define, and you have to justify. You have to justify your equation with some physical laws. In this case, Newton's laws. I think that's in this particular case, that's the difference between physics and maths. Physics is specific to our universe. Math is general case for any hypothetical universe. True, true. You can define it like that. That's a good definition. I'd say it's not a definition though. It's a description of physics and maths. Comparison. Problem 3. A proton is fired with speed v directly at a helium nucleus. Find the velocities of both particles when the proton is at closest approach. So this is quite... What was I thinking when when I wrote this question? Let me check my notes. Oh yeah. Okay, that's we're not looking for the closest approach. Of course, we're looking at the velocities at the closest approach. Oh, that is beautiful. That is a beautiful problem because when you read this question at first, you think that it is a question about electric fields, and it is not. Okay, so we have an alpha particle, which is a helium nucleus, which is relatively big. And there's a helium nucleus, which is stationary. And there's an alpha part, a proton is traveling. So it's a proton traveling with speed v. Now, if you know anything about protons and alpha particles, you will know that the mass of a proton is m. If the mass of the proton is m, the mass of the alpha particle is 4m. Okay. Now, as they approach, the helium nucleus is positive, and the proton is positive, of course. So they repel. So at some point, the proton is at closest approach. It's positive. They're repelling. And their relative velocity is 0. Relative velocity is 0 at closest approach. That means that the velocity of the proton is equal to the velocity of the helium particle. Does that make sense? Do I need to clarify what this means? Closest approach is the shortest distance. Yeah, but we're not looking for that shortest distance. Yes. So we are there. The question is, what happens when they are closest? So the helium nucleus is stationary, and the proton is approaching it. And the helium particle starts to accelerate. So it goes like this. So the proton will keep pushing, and the helium will accelerate away. And when the proton is the closest, that's where they have the same velocity. They have the same velocity. Let's call this velocity V1. V1. So at closest approach, both travel at V1. Okay. Find the velocities of both particles when they are at close approach. So find V1. That's what we need to do. So we write down the conservation of momentum. So mv plus 4m times 0, because it's stationary, equals mv1 plus 4mv1. So we can cancel the m's. So v is equal to v1 plus 4v1. So v1 is equal to 1/5 of v, and that's it. I love this question because if you Google closest approach, you will see bizarre you will see equations like this. So to find the closest approach, you have 1/2 mv squared is equal to 1/4 pi epsilon 0, and this is going to be E times 4E divided by by D squared, and D squared is the closest approach. So if you rearrange that, you can find D. You can find the closest approach of the two particles, but yeah. It would be very interesting to find the closest approach. As a matter of fact, no, this would not give you the closest approach, because you would need also 1/2 times 5m v1. Yes, you can. So you can find the closest approach from here, from this equation. I'll leave it to you as an exercise. Also, try to figure out what this means. This is an energy. No, a SUVAT would not be applicable here, and somebody tell me why. Thank you. Acceleration is not constant. Thank you very much. Yeah, acceleration is not constant because the force depends on the distance between the particles. The closer the particles are, the stronger the force. And if you consider springs, the more you compress the spring, the stronger the force. That's linear. And with charged particles, it's a quadratic relationship. So the force increases as the inverse square of the distance between the particles. So it's a very non-linear, it's a very non-uniform acceleration. Okay, problem 4. It's another amazing question. Two charged particles, A and B, have mass m and 2m respectively. So A has a mass of m, and B has a mass of 2m. Have equal but opposite momentum. When t is 0, the particles are at positions shown. The trajectory of particle B is given. So particle B travels like this and then goes away. Draw the trajectory of particle A. Okay. I really like this question because there's so much to think about here. So can somebody give me a hint? Inverse, but scaled differently. Well, true. What is your reasoning, Alistair? The total momentum is 0. Very good. The total momentum is 0. That means at any point, the particles will move in exactly opposite directions. Yes. Momentum is constant at any moment in time. So momentum, total momentum is 0. So that means at any moment in time, the velocities are exactly opposite. That means that the final velocity of A is this way. So when B is going this way, A is going that way. When B is going that way, A is going that way. So, but also M is traveling faster. If B is traveling with velocity V, A has to be traveling with velocity 2V. So it's twice as fast. Therefore, it will travel in a bigger circle, but will end up traveling in exactly opposite direction to B. So this is how we draw it. So the trajectories will be parallel because the total momentum has to be 0. That means that if when momentum of A is equal minus the momentum of B. And these change. These change. So when P2, PA is this way, PB is this way. If this is PA, this is PB. They have to add up to 0. So when A is traveling this way, B is traveling this way. Because otherwise they would not cancel out. Okay, moving on. Problem 5 and problem 6. Problem 5 is a center of mass question, as a matter of fact. You will need to use center of mass quite often, but let's move on to question 6. And then if we have time, go back to question 5. Okay, so a projectile of mass 0.2 kilograms and speed 122 meters per second hits a ball of mass 12 kilograms, hanging on a massless string of fixed length. Okay. The projectile was moving at the height of the center of the ball, and after hitting the ball, stops inside the ball. Why is this important? The projectile is moving at this height of the center of the ball. Why is this? Why did they mention that? Can somebody tell me? If you ever play snooker, you would know that if you don't hit the ball in the center, it will start spinning. So Alistair, well done. Yes. You can do a forward spin, side spin, back spin, whatever spin. So that's a very similar situation. If the projectile hits the ball, for example, here, the ball will start spinning forwards, and some of the energy would go into spinning of the ball. And yeah, so the central hit ensures that there's no spin on the heavy ball. This is called a ballistic pendulum. Ballistic pendulum. What it is designed for, it is designed to measure the speed of bullets. Now, this is a very simplified version of a ballistic pendulum, but basically, yes, that is how you measure the speed of a bullet. Because what happens, you know that the bullet hits that, you have conservation of momentum, and then the pendulum would go up to some level. So you can work out the initial kinetic, so you have the potential energy, the potential energy of the ball, because it goes to a certain height. And using that height, you can work out the initial velocity of the bullet. Okay, and because the pendulum starts swinging, you can measure the height more accurately because it reaches the height several times as you go. Basically, the pendulum starts swinging, and all you need is the amplitude of that swing. Okay, this is an experiment. Anyways, the projectile of mass 0.2 kilograms hits a ball. So first, conservation of momentum. Conservation of momentum. MV, well, let's say MU is equal to, so it's traveling with velocity U. Once it hits, it gets embedded. So it becomes part of the ball. And together with the ball, they travel with velocity V. So M plus M V. Does this equation make sense, or do I need to clarify why? Momentum before, momentum after. So before it's MU, and after it's the total mass of M plus MV. If you need me to clarify this, please let me know. Momentum before is mu, and momentum after, now we have the ball and the bullet both traveling with velocity v, so it's m plus mv. Right. M is the mass of the heavy ball. The projectile stops inside the ball. What is the maximum height that the ball can reach? So we have conservation of energy. Conservation of energy. So 1/2 m plus m v squared. That's the energy. That's the kinetic energy of the ball and bullet after they swing, and it's equal to m plus m gh is equal to the potential energy at the top. So GPE at the top is equal to the kinetic energy at the bottom. Okay. So m plus m cancels. We have h is equal to v squared divided by 2g. And from here, v is mu divided by m plus m. So we plug that in, it's equal to m squared u squared divided by m plus m squared multiplied by 2g. And all you need is to put stuff in. So 0.2 squared times 122 squared divided by 12 plus 0.2, so 12.2 squared multiplied by 20, just for simplicity. And we get a number 2 squared 2 squared times. Yeah, that's what we assumed. Yes, kinetic energy. Oh, why we can assume that the potential energy are the same. Okay, so at the beginning, when the bullet just hit the pendulum, the gravitational potential energy is 0, and the kinetic energy is 1/2 mv squared. At the top, GPE is equal to mgh, and kinetic energy is 0. So we have the total is equal to the total. So basically 0 plus 1/2. Well, and it's not m star, 1/2 m plus m v squared is equal to m plus m gh plus 0. Yeah. And 122 squared divided by 12.2 squared times 20. 0.2 meters. 0.2 meters. Now, please note that the kinetic energy of the initial kinetic energy of the bullet is not equal to the, so kinetic energy is not conserved. Please note kinetic energy is not conserved. Can somebody tell me the reason why it is not conserved? Or how do you know that the kinetic energy is not conserved without doing any calculations? It is an inelastic collision, but what does that mean in terms of energy? Nothing to do with mass, Alistair. Energy lost in collision, what does that mean? Object is deformed, Louis. Yes, well done. When the bullet is embedded in the ball will be deformed. Yes, it causes damage to the ball. So energy is transferred to thermal energy as the object is deformed, and the bullet is deformed, of course. Therefore, there's heat being released. But we are not relying on the conservation of kinetic energy during the collision. We are relying on the conservation of momentum, and this is why this method is a valid method. So this is called the ballistic pendulum again, and it is used to measure the velocity of bullets or small projectiles in general, usually bullets. Okay. Now this is not exactly a conservation of momentum problem. It used to be, but I've simplified it a little bit. The question was, when the velocity of the surface of the liquid is v, find the velocity of the trolley. Okay, anyways, the trolley of mass m and length L. So we have the length of the trolley. Contains a liquid of mass m in the left cylinder. So there's a liquid of mass m. The tap is opened. Find the displacement of the trolley once the liquid levels out. So the liquid will keep pouring until it's equal level. The cylinders are thin compared to the length of the trolley. Okay. And there is no friction. So who can tell me why would the trolley move in the first place? Very good, Alistair. The center of mass cannot change. Therefore, the trolley would move slightly to the left because the liquid would displace to the right. Therefore, the whole trolley must displace to the left. So center of mass cannot change. Cannot change position as there are no external forces. External forces. Very good. So we can draw that. X and well, let's say this is 0 on the trolley. So X center of mass is equal to the mass of mass of the trolley multiplied by the position of the trolley, which is 0, plus mass of the liquid, which is small m, multiplied the position of the liquid, and in this case is minus L over 2. Yeah, so the liquid is minus L over 2. That's the position of the liquid, divided by m plus n. So this is before. and then after. So X center of mass is equal to, now let's say that the trolley has moved by X. Trolley has moved X meters to the left. Trolley moved X to the left. So it's going to be M multiplied by minus X plus small m. Well, because the liquid will be even out, so the center of the mass of the liquid will coincide with the center of mass of the trolley. So minus X. Okay. The center of mass of the trolley will coincide with the center of mass of the liquid. Therefore, divided by m plus m. And now we have this is equal to that. They have to be equal. So m times 0 plus m times minus L over 2. We can ignore the denominators, equal m times minus x plus m times minus x. So this goes to the left, this goes to the right. So we have m plus m x is equal to ml over 2. So x is equal to ml over 2 m plus m. Okay, that's about it for that question. Okay, we will have another webinar because the assignment is posted on Google Classroom. The due date is the 26th of February. So you have 4 weeks to do it. Okay. And it's slightly bigger, 14 questions. And as I said, I challenge you to solve problem 14, which is difficult, and send me the solution before the next webinar or on the webinar. Yeah, you can send it in Slack in the general channel. Okay, so we'll finish here. I hope this was useful, and I'll see you next week. Bye.